So next we're going to talk about sex-linked genetic disorders. So sex-linked genetic disorders have inheritance patterns. So at this, you have seen before this Punnett square. So you have seen this before, and that's I showed you the math on this when we said there's a 50% chance the child is going to be girl and there's a 50% chance it's boy. So just to remind you guys, females have two X chromosomes, XX, and males have X and a Y, so X and a Y. This Punnett square is showing that, so you do the math, you put XX up here, XY here, and it shows you there's a 50% chance the offspring is a female and there's a 50% chance the offspring is a male. So for males, there's one X chromosome. And this is when I mentioned that some insurance companies have this data. They say the males die at younger rate, they have a high mortality rate. And one of the reasons was they have only one X chromosome. They don't have a backup. If something goes wrong with the X chromosome, they're probably going to be sick or they're going to have the disorder, and then that might cause death. Whereas females, they have two X chromosomes. So in this example, this is called X-linked recessive disorders, and it says it affects more males and then females. And again, the reason for that is because males have only one X. They don't have a backup. So therefore, if they have it on the X chromosome, that means they have the genetic disorder. Whereas females, they have two X's. If one of them is, not good, little h is showing affected, big H is showing healthy, they're still just a carrier. They're not full-blown sick. So in this example, these are the male gametes. Male gametes are healthy, big H is healthy, and then you have the Y, female, she's a carrier. So the chances that you're going to have a, healthy daughter, non-carriers, 25%, a carrier daughter, again, 25%. Here, you have a 25% chance the son is going to be healthy, and 25, the son is going to be sick. When I say 25, I'm comparing all daughters and sons. Sometimes if the question is saying, what is the chances that the son is going to be sick, then you're just looking at the sons, then it's 50% for each. So I have a question for you guys that I want you to work on. So females, in order for them to be sick, they need to receive recessive allele on both of the X chromosomes. If it's just one, then they're just carriers. Males, they only have one X chromosome. To express the recessive disorder, they only need one X-linked recessive allele, and they're going to be sick. So that's the question I have for you guys. I'm going to give you a few minutes. Do a Punnett square and tell me the answer in the chat. Okay, so most of you said C. Actually, everybody said C. If anyone is still not sure how to get this, the answer is C. I can show them. So let me know. Anybody needs me to work on this problem?
Yes, please.
Okay. Okay, so let's read the question. Color vision is controlled by X-linked gene. So we're working with the X-linked gene. With color blindness being recessive to full color vision. If a colorblind mother and father with a full color vision. So mother is colorblind, so I'm gonna say big C for healthy and then little c for sick. So she is colorblind completely. That means she has to have both small c's. So I'm saying big C, healthy, and then little c for affected. So mother is colorblind. That means she has little c, little c. Father is healthy. He has one big C and then Y. Then you do the Punnett square. You have big C, little c, big C from the father, and then little c from the mother. It goes down. And same thing here, you bring the little c down and Y, and then little c down and Y. These are the daughters, and these are the sons. When you look at the daughters, they have only one little c. That means they're carriers, they're not sick. And then when you look at the sons, they both have little c's. So all the boys are colorblind because they have the affected X. So first answer says 75% of the boys will be colorblind. No, that's not true. There, it doesn't even show 75%. 50% of the boys and 50% of the girls will be colorblind. This part is true. Boys are colorblind, but the girls are not. They are carriers. All the boys will be colorblind and none of the girls. That's true. This is the answer. And then it says 25% of the girls will be colorblind. That's not true. They're just carriers. So colorblindness is, does that make sense now? The people who, yes, okay. So people who are colorblind, mostly you're going to notice that it's males, and that's because they only have one X, there's no backup. Females, you're rarely gonna see that they are colorblind, because in order for them to be colorblind, they need to have two small C's. That means their father is colorblind and their mother is colorblind, and they got the affected X chromosomes. So mostly you're going to notice that males. Another example I showed you last time was the pedigree analysis for the royal family of England. This is the one I showed you. So in the this pedigree analysis, we talked about hemophilia. So that's another example of X-linked. Queen Victoria was the carrier for that. She wasn't full-blown sick, but she had, some genes that affected her a little maybe. Then you're noticing the circles are females, the squares are males. You're noticing males, they're full-blown sick. Not all of them, but whoever got that, they're full-blown sick. And the females, they're mostly carriers because the father was healthy. So females, if they got affected gene, it was only from the mother. And then the other gene was healthy from the father, therefore they're the carriers. Whereas males, they got maybe one X, the affected one from the mother, and the father was healthy. So they're full-blown sick. So it's all fully, filled in. So that's hemophilia for the X-linked. There are some more. I don't need you guys to memorize the names or even the chart. This is just showing the examples. I showed you hemophilia example for the royal family, and we just did a question with the color blindness, but there are some other disorders that are also X-linked. And then this was for recessive allele, and then here is for the dominant allele. So there are some you can kind of read on it if you are interested in this, but I don't expect you guys to memorize the chart or even all these names. These are just examples. And then we talked about CC the cat. Yes, truth. We're going to talk about that. You can track down sick genes or mutated genes that are causing the disease. So CC the cat, and I think CC stands for carbon copy. And then I showed you this photo, and I said they took some skin cells from the mother, or not the mother, I wouldn't say mother in this case, they're more like twins, from this cat, and they cloned them, and they got this cat. This cat looks different than this cat. So how does that happen? That's what we're gonna look at. So here, this cat has genes for both black fur and brown fur. But in this cat, this is the one that gets activated in this area. So she gets black fur there and the brown fur activated in this area. So that's brown fur there. So the genes has to be activated in order for her to get the same same genes have to be activated in order for her to look the same, but that doesn't happen. Even if she has the same genetic material, depending on which genes activate, she's still gonna look completely different than the parent, or if it's a if it's a cloned one, then from the one original one. So if one X chromosome has allele for orange fur, the other has allele for black fur, color patterns emerge when X chromosomes are randomly inactivated or activated. So you see that. So this is called X inactivation. X inactivation. It can prevent the double dosing of proteins, means not both of them activate in that area. Otherwise, it will just confuse your body. So people who have maybe had their cat for a long, long time, and then maybe they know the cat's about to die. Now they go ahead and they spend thousands of dollars and they try to get their cat cloned. So they can take some stem cells from that cat that's about to die and they can get a cloned cat. So basically, that cloned cat, it probably won't even look the same as the cat they had, because different genes will be activating in that cat. And so they don't have, just because they got the stem cells from their old cat doesn't mean they had the same cat. It just had the same genetic material, but that's basically sister of their original cat. Another thing is, if you're taking stem cells from a cat that's already old, there's a higher chance for mutated genes and for maybe cancerous cells. So it's not healthy. It's not very healthy if it's already old.